So I'm not very good at clickers, but so this presentation is called Matryoshka. And in case you don't know what is, well, first of all, I'm Eduardo Vela. My nickname is Zero Dark Cat. I have a Twitter account that I don't use, but you are free to follow me. So I like researching web application security stuff. I wrote a book with Mario and a couple of friends, Gareth, which couldn't be here, and David, who is at home. I'm the TLM of Google's PSIRT, which is like web or and we call it Whoops because we have a bug, Whoops. And it's like whenever we receive a security bug from someone external, we investigate it and do some stuff. And a lot of the things we do are kind of researchy because we try to find out what is the root cause of the bug and what's going on and so on. Anyways, so this talk is about what vulnerabilities someone that is following the best practices in the general sense is most likely to be vulnerable. And this comes from the fact that when we audit some of the applications, some of the bugs that they have are something that are not just like, oh, they forgot to do input validation, or oh, they forgot to do this, or they are using the wrong libraries, or they are using the tools wrong, etc. It's mostly something that seems to happen very, very often. Like, it seems to be the case that people make the same mistakes again and again and again, which is the same as normal security, but in this case, they are anti-patterns that we don't see very often. Well, we didn't used to see very often a couple of years ago. The warning is that this has implicit bias towards very HTML5-ish type of applications, which is like very JavaScript using new APIs, post message type of things. And I'm only discussing attacks and exploits. I might mention some stuff about preventing, but in general, I'm not going to focus too much time on that. I'm mostly going to be saying this thing is broken and now someone has to fix it. And some of the bugs might be known by some people because they are actually common anti-patterns. And yeah, so I'm presenting 4 of them. I had like 6, but then I figured that I had too many slides. In case you don't know, this is a Matryoshka. It's like a Russian doll that has another Russian doll inside it when you open it, and it goes until there is a very small one that you cannot open. So Best Practice Joe is a guy called Joe, which follows his best practices. And these are examples of the type of things that he does. He usually uses strict contextual auto-escaping for mixing user input. He uses stuff like all the JavaScript and CSS is static. He uses content security policy. He uses all the fancy HTTP headers that Microsoft introduced. He has caching headers and etc. He has users to upgrade their browser using unsupported one. No one ever does that, but let's say this guy does. He blocks access to unused plugins using the requested with thing. Like there is no CSR box, etc., etc. Right? Like access control is everything is perfect in this guy. So this is scroll bars. So how many people use scroll bars? All right. So I will not explain what is scroll bar. So scroll bars. One thing that happens in the way that the browsers work is that evilwebsite.com iframes mybank.com, evilwebsite.com can make mybank.com's scroll bars beautiful. And evilwebsite.com can deduce when my bank needs a scroll bar. And this is used by some websites to ensure that there are no scroll bars because that looks ugly. So they set a scroll bar, they detect their scroll bar, and then they keep increasing the height until there is no scroll bar, which is kind of an info leak, but it's an info leak that is used by normal people for some reason. Anyways, but the end result is that evilwebsite.com can know the exact height and width of the page layout. So there is an attack that you can do, which is you resize the iframe to the maximum width possible, and the height to the smallest width without a scroll bar. So that means this will be infinity, and at this point, this is the bare minimum before this scroll bar shows up. Then what happens is that you reduce the width a little bit, and that will introduce a scroll bar. And that will, because if you notice here, this is going to overflow to the next line. If you notice, you see, bond is here and now is there. And that introduces a scroll bar because this size doesn't, because this doesn't grow, right? So is that clear? Like, you introduce a new scroll bar, and then now you can detect that it exists. Step 2 is that you increase the height until there is no more scroll bar, and then you do it like that, and then you repeat. So then what you get is like this width and this height, and that's it. Now if you get the width of a step 3 minus the width in a step 1, you can know the width of the word bond. So this is just being able to know how long is bond. In retrospect, you could say like, oh, you can know how many letters there are, how many characters per letter. But in fact, most fonts have a different length for each letter. So if you have, except for fixed width ones, which by definition have fixed width, each character has a different width. And this allows you to extract the width of the letters in a word. However, you don't get control of the order of the. So, anyways, if you repeat, so in this case, you can extract Bond, and then you extract James, and then that will extract Iceland, then Bond, then the, then is, then on, then name, then is, then secret, then my, then there, then hello. So you don't get them in order. You get them in a very weird, funky order. But anyway, so because you get as I was mentioning earlier, every letter has a different width, and because you get the width and the height, then this is different than this one. So you know that this one, you don't know actually the value, but you know the length. And if you have a database of all the fonts and the letters of the width of the letters, then you can figure out more or less what it says. Anyways, the second problem is that once that all the words are compact together, then you get the case that S overflows over the second letter. Like now, letters start overflowing as well, and now you do the same trick to calculate each of the letters. So the end result, So the end result is that you can figure out the order of the letters, but now you don't know the order of which. You don't know which word was the one that overflowed that ended up causing that error. But you can figure it out because of the width. But anyways, it doesn't matter. So you don't know. You kind of know the values, but you don't know in what position they are, and so on. This is a subset of the NAPSPAC problem, if you are familiar with that. So, yeah, in most fonts, each letter has an almost unique width. In the cases where it's not, you reduce your possibilities to letter choices. And when you cannot learn the order of the letters or the order of the words, you can figure out very closely what they mean. And in particular, this is particularly bad for JSON responses. So that means that because the JSON responses usually know the height, the width, of each key value pair, you know the value of the keys, but you know the value of the value. So then you can just remove all the keys that you know, and then you just one by one extract the values. So we can call this wrapping overflow leak on frames, because I like wolf and crime, breach, all of those. I want a name that is fancy. The workers are so ways to mitigate it is with extreme options in I. And in retrospect, iframes sound like a terrible idea, so we should travel back in time and prevent them from happening. And another way to prevent it is by having scroll bars internally that don't allow you to wrap stuff, which is how a lot of people, how we ended up fixing in a lot of cases. This guy, that was the first part. This guy is Jason, and he's confused. So this is a confused JSON putty. So JSONP callbacks are cool, and people whitelist scripts that are JSONP endpoints. And this is not only for content security policy. This is also for things like, I don't know, people just allow iframes, not iframes, and script source from arbitrary domains in some cases for bad reasons. But they think that it's okay because they control the values there. However, you have JSONP, but what can you do with a single function called with an argument you can control? And that's like an interesting question. So what can you do with just a single function? And one thing that we noticed was, or Pavel Toporkov, I hope I pronounced his name right, had the idea of something like reverse clickjacking. So this is like actually ended up being kind of powerful, because the proof of concept that he got was like effectively was enabling some settings that made everything public, which is very bad. And he was just doing he was opening a window, making the exploit there, And then the callback was opener.frames.blah.document.links.one3.click, .pricing.show, .lems.click, .forms.submit. And it's almost as good as an XSS. No need for insert interaction, no need for iframes, and XRAM options won't help you. So that was a cool attack. And almost all interaction actions are reachable with clicks. There are some cases that, for example, changing your password actually requires to type your new password. So this exploit is not really a problem there. But yeah, so its content security policy is very bad if you always allow a JSONP endpoint, which is obvious. Unfortunately, you cannot do, in some cases, some services have widgets that you have to whitelist for a script source, like ads or like social media widgets or stuff. And those end up having JSONP endpoints in the same host where they host the script. And because that happens, then I as a website owner cannot really prevent these other third parties from affecting my website. In theory, you could use CORS to avoid using JSONP, but not everyone does that, unfortunately. That's the evil mailman. That's the next part. So lack of JavaScript types. That's also kind of obvious. If in JavaScript we don't have types, and because we don't have types, we need something like to validate the types, and we have something that is like JSON format validator. We would like to have something that is like a JSON format validator, which is something like verifies that a JSON or like an object follows some specific spec. But unfortunately, as far as I know, there is no way to do this in the browser. So you have to do it manually, which is work, and then it costs performance, and because it costs performance, developers don't like it, and because they don't like it, they don't never do it, and because they never do it, they never check the types they get. So this is obviously a problem, but the ways to exploit it that we came up with. Well, first of all, there is something called transferables. In new browsers, there is post message can transfer not only objects, but specific new type of things like byte arrays and stuff like that. And date is one of them, for example. So in this case, you can do something like inheritance. So in this case, you do JSON.parse over what, and this property is called proto. This generates an object from a null prototype. And then you change the proto value to be a date, and then you post message of X. And then the other window actually receives X that is supposed to be a date, but that actually you can override properties on it, which is kind of bad for, which is kind of bad for stuff like strings and arrays and etc. Because now you can send something that looks like a string. So even if you do something like instance of blah, 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 then you can still bypass a lot of the things that you get. Another trick is that when sanitizing for performance reasons, it's actually faster to check for index of and then replace only if needed. And this is a very common anti-pattern. We found it in a couple libraries. And so you have an input, which is variable, and people check index of angle bracket. And if there is no angle bracket, if there is an angle bracket, then replace, otherwise they don't replace. And this is faster than a regular expression over all the input for some reason. However, if you send an array, then this is not going to match because now index of is matching full strings, and that doesn't work either. So that's one way to exploit it. Other exploit, which is one is slightly more interesting, you can control how your objects aren't serialized as a string. So if you do it like that, then this is going to throw an exception, cannot convert object to primitive value. However, the interesting part is that you can also make your code work in some cases but fail in others, which is pretty cool. So for example, if you have an array that is an array of an array, an array that has an array, that has an array, that has an array, that has an array, like 10,000 times, then this is going to fail for functions that are very deep in recursion, because what ends up happening is that when you try to serialize the topmost array, you try to serialize another array, and blah, 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 eventually until you get hello. And there's a lot of things that trigger this behavior, comparing, escaping, test, etc. All of them force string serialization. So what you can do is, like, if you have ever seen a pattern like this, which is actually common as well, is to do window.username. We first assign a variable to some malicious variable. Then you check if you check it for a regular expression or whatever. And if it doesn't match, or if it matches, then you do HTML escape on whatever. However, because this is a level of recursion deeper, this is going to fail. And now window.username is, is a bad one. All right, now the next one. This is timing and fork or something like that. I don't remember. What a fork. All right, so web application timing. It seems to be on how do you call this? It seems to be like the thing of the day because everyone is talking about timing. But it turns out that you can measure string comparisons and regular expression matches byte by byte between two web applications. So in this case, instead of attacking the browser or the network stack or the operating system or whatever, you actually attack another web application, which in this case is not controlled by the browser. And turns out that you can actually measure string comparison. So the reason that this works is because the browser JavaScript execution is single-threaded, which means that events and scripts in different windows and so on are, well, this is kind of complicated. It's in the same process, but anyways. So assume that events and scripts in different windows are thread safe, and never two scripts will run simultaneously. And because two scripts will never run simultaneously, that means that whenever you are not running, someone else is running, or no one is running. So this is true even for Windows across origins. So if a script in evil.com is running, that logs execution of scripts in good.com. And if good.com is running, then I don't get executed for that time. So the way that you attack this is you attack a string comparison like this. So this stuff becomes possible. So now you can compare. I don't know if you are familiar with normal crypto type of signature comparison type of attacks, but this type of things is no in normal JavaScript, in normal code. And in JavaScript, we probably didn't think about it that much, but we should think about it. So we calculate in which specific byte we failed by measuring how long it takes to reverse it to make the comparison. So if it takes the browser a lot of time to fail, that means that you got, not a lot of time, but a little bit of time to fail. That means that you got a string that looks more like the other string. So hello is equal to help takes longer to compare than hello is equal to xx, because hello is equal to xx is not even the right length. So it fails very quickly, while hello is equal to help doesn't know that it failed until it goes to the last possible byte. And this happens really fast. Imagine, comparing small strings is like super fast. So we need a lot of comparisons to be able to measure it. And we also have an API that is performance.now, which is super cool because it's super fine-grained and it gives you like very, very precise timing on how long something takes to happen. Oh, it doesn't work. Oh, all right. Take that. So it's possible to attack things like events and inline scripts with history back forward. So to explain events is stuff like post message. Whenever you have post message, it's very common to have a secret in the post message fields, and you compare it with some secret that you have in memory, and then if this doesn't match, then you throw. And this happens this is very common because you're trying to prevent against confused deputy type of attacks in post message. And if you don't use it, then you should be using it. And the other type of attacks that you can do is inline scripts. So what you do is that you open a victim side, you navigate it again, and then you do history.back and forward. And then when you do back and forward, that makes the site load from cache instead of making a network request. So that removes the network request latency factor from for the thing. And you can compare, you can imagine anything that you can steal. I've noticed this being used to compare strings, cookies, tokens, CSRF tokens, and etc. OWASP tokens, that was very bad. Right, so sample attack against post message. This is like the easiest one to exploit. You measured performance not now. You send like 1,000 or 2,000 messages to the victim, and then you send one message to yourself, all of them in the same thread. What is going to happen is that the browser is going to schedule 1,000 events, 1,001 event. 1,000 events are going to be sent to the other side, 1,001 events is going to be sent to you, and then you measure the time that it took from going from 1 to 3, and then you divide them by 1,000. That's how long it took the browser to execute the comparison. By the way, performance.now goes to microseconds, so you actually get very good. Yeah. Anyway, so you repeat a couple hundred times so that you repeat this experiment a lot of times so that you verify that you are not, like the browser didn't start garbage collecting in the middle or stuff like that. So for string comparison, to make it exploitable, you first need to guess the string length. Browsers actually, the way that it works is the browser usually checks for that the string length is the same that the thing that you're comparing it to, and if it's the same, then it just fails quickly. So you first need to guess the string length. So you make a lot of guesses, and then eventually the one that took logs to compare is the one that is the right string length. And the reason it works is because it compares the string length and it goes into another loop where it starts trying to compare byte by byte, and then it's going to fail in the first byte, but that's okay. When we calculate the first byte, the attack works better if you calculate timing for 2 bytes at a time. So if you only do 1 byte at a time, then the difference between a correct result and an invalid result is very small, so it's very hard to measure. It's still possible, but then you need more and more requests, which makes the attack take a lot longer. So this one actually is faster to run. And then, so you execute everything, you order by median, and then that gives you the first. Once you order it, it's going to be something like T, TO, TU, TU, TC. And the reason that works is because T is obviously the most. You can do something called a student test. Well, you do some statistic test to compare if there's a significant difference in the timing of whenever the first byte is T or is X or whatever. And now you get the first T, and then you brute force based on the results on the previous operation. So if you notice here, it started with TI. So you first start TIA, TIB, TI, etc. And then the second one was to TO. So then you TOA, TOB, all the way to TOZ, and so on and so on. You sort by. So you sort by the median again, and then you repeat the same attack, blah, 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 and eventually you get the value that you're comparing. It's surprisingly simple. On slow computers, the attack becomes a lot less reliable. So the faster the computer, the more reliable it is. You just need to send more tests, but that's okay, because instead of sending 1,000, you send like 10,000, but they are going to be very fast, and they are going to be very accurate. And now, the interesting, cool thing about this is that if you have ever seen a movie where they are cracking a password, the password is cracking 1 byte at a time, and it eventually gets a password, like the movie that just came out, Olympus Has Fallen, they probably were using an attack like this, so that's cool. Anyways, so I finished very quickly. Anyway, so to recap, wrapping overflow, leaks on frames, range by char, confused deputy, JSON putty, reverse clickjacking, evil mailman, lack of types, web application timing attacks. And I speak really fast. If you want to go back, talk now. Otherwise, I'll continue reading about other stuff. No one? No questions? I have like 20 more slides because I knew this was going to happen. All right. So. Okay, so we talked about evil mailman. This is zombie mailman. It seems everyone is post message. I don't like post message. Every implementation I've reviewed, either by fun, that's not fun. Well, by I don't know, just in my free time, has done stuff wrong. So there is one that is very popular that is called ECXDM that was vulnerable to several things. Then there is also the Facebook one, and then Google ones, and etc. So yeah, that one is, bus message is hard. It's a Firehouse API, which means that everyone has to use the same channel to do everything. There is no transport or presentation level type of API abstraction. Well, now there is with something called channel messaging, but before there wasn't, and people still don't use it. So because actually Firefox doesn't implement it, and because Firefox doesn't implement it, no one uses it. So, and Firefox doesn't want to implement it because no one uses it. So that's funny. Anyway, so this one API, which must be shared across server screen, perform with cross-window communication. So if you have a Facebook button, a Twitter button, a Google Plus One button, and whatever, then all of them use the same API to talk with the parent page and to the ads, and they talk to like everything, and they don't work so well together. Actually, in some cases, they interfere with each other and they break functionally. But I'm more interested in the cases where they break in security problems. So it's very common to have code for callbacks and timers and etc. Pretty much every library has something like this. Say like, hey, I'm here, and it's like, oh, okay, you're there. And what they do is they do some sort of version of this code. So they just either transport messages at either data, and this one can be either star or slash or the source origin, but then it's different. Either way, you can attack it. So this leads to info leaks and CSRF style of attacks. And the reason that happens is that info leak is obvious, right? Because you just force someone to post to that window something, and then when they reply to you instead of them, which I will explain how to exploit that in a second. But and also CSRF type of attacks, because then you send the message, and then when it replies, it's not going to go to you, it's going to go to someone else, and it's the same exploit. The way that you make e.source go to a different window. So this is how it works. If you want, for people that use e.source, you just do unload victim win.post message equal to whatever, and then when they do e.source.post message, that's going to end up, the message is going to end up in the victim side, not in your side, and that's bad. So yeah. There's other ways of doing this, sub iframes. So this is something that also comes up often. So evil.com, iframes good.com, good.com, iframes. So evil.com is my evil website. Good.com is a good website. Hello.com is another website that trusts good.com. So because evil.com is the parent frame of hello and good, then they can navigate hello.com to buy.com, for example. What ends up happening in this case is that hello.com is iframe by good.com, which is not expected. Like, you usually don't expect to be iframe by a semi-trustworthy type of website, while not in an unexpected way. And the reason that is bad is because then you can do this type of attacks, which, oh wait, not this one. Anyways, so you can do attacks where you can do something like parent.postMessage or parent.framesx.postMessage type of thing. So right, that's an example. Internet Explorer has a problem with the way that it deals with postmessage in open and opener. So people have to do things like open and then create a frame and then postmessage to that frame, or they have to open a parent and then from the parent do the postmessage. In those cases, you can always control who you send the message to, which is the same problem. And to prevent those type of problems, you have to use channel messaging, which is cool, except that Firefox doesn't support it. And this is one way of doing it, for example. Another thing is that people sometimes do fuzzy matches on e.origin, so they use ERL.parsing libraries. So for example, if you parse the URL, parsed scheme is HTTPS, and then you check that the list of hostnames that you approve are in parse.hostname, that's safe. However, this happens, I've only seen it happening twice, but I thought was interesting. So because you read that, so you can send a message that whose origin is null, and because when you parse URI.parse null, that makes it a relative URL, and because it's a relative URL, then the location, the hostname of that URL is going to be the same as location.hostname, and then you exploit it. So yeah, and that's about it. Well, that was not 20 slides. Anyways, all right, that's it. No more questions? Actually, no first questions? All right, thank you very much.